Hi everyone. This unit that we're in, the title of that unit is Quadratic and Square Root Functions. And up until now in this unit, we've talked a lot about quadratic functions. We've factored them many different ways. Recently, we solved quadratic and actually some cubic functions by factoring. And so now what we're going to do is we're going to shift more into the roots part of this unit. And we start out by talking about radicals and operations with something called complex numbers. Now, complex numbers, it's kind of a complex thing. You have heard, hopefully, in math classes about different types of numbers, and maybe you don't know what they are, but you've heard the words. So maybe you've heard integers. Well, integers are the set of all counting numbers and their opposites. So like -3, -2, -1, 0, 1, 2, and so on. You might have heard about whole numbers. So those are 0, 1, 2, 3, and so on. You might have heard of natural numbers like the counting numbers. So that would be 1, 2, 3, 4. You might have heard about real numbers. Real numbers are all of the numbers that combine integers, whole numbers, natural numbers, and everything in between. So that involves fractions and decimals and things like that. But then we have complex numbers. And what complex numbers look like is something that doesn't fit inside of the real numbers on a nice number line. So it'd be like the square root of -25. And up until now, in a math class, you have not been able to find the square root of -25 because the answer is things that doesn't exist, or that's not a real number, or the world explodes. That's what I used to tell my students. So you couldn't have the square root of a negative number because that wasn't possible until today. So now we're going to talk about complex numbers, and our essential questions are: what is an imaginary number? Imaginary and complex are synonyms. So what is an imaginary number? How do we use it when simplifying radicals? And in general, how do we simplify radicals? So go ahead and copy your essential questions. What is an imaginary number? How do we use it when simplifying radicals? And finally, how do we simplify radicals? Okay. So there's no great place to start when describing complex numbers, so I'm just going to describe what you see next in your notes. It says the powers of I repeat in a definite pattern. I means a complex component to your number. Component means piece. So I just means like there's a complex or imaginary piece to your number. For example, I know the square root of 25 is 5, but because I've got a negative in here, that means that there's an I somewhere in my answer, because that I means there's a complex or an imaginary part to my answer. So 5 is one part because that's the square root of 25, but there is an I in there as well. So we'll get back to this in a moment. What I'd like for you to do is take your highlighter tool or some kind of colored something, and this box and really this box are pretty important, and you need to make them stand out. It says you need to remember that I is equal to the square root of -1. I is the square root of -1. This is what you need to know from today. And for this pen to go in the trash can, new red pen. Ah, that looks better. All right, so you need to remember that I is equal to the square root. That's what makes the complex or imaginary part of the answer. It says, think about what happens when I is raised to a given power. So if I is equal to the square root of -1 and you square that, what happens when you square a square root? Well, when you square a square root, both of them cancel out. They're inverse operations. And so the only thing that's left is the negative, which is why I squared is equal to negative. So if you look above, you'll notice in the powers of I repeat in a definite pattern. So I is just I. I squared is -1. So we found that out here. I cubed is -I. I to the power of 4 is 1. So think about, to get I cubed, you multiply I and I squared, right? Well, I times -1 is -I. That's how we get I cubed. And then here, to get I to the power of 4, you can either multiply I times -I, or you can multiply -1 times -1, and you will still get 1. And then they start repeating over again. I, -1, -I, 1, and so on. So this is something that you will want to try and commit to memory, and it will be easier the more examples that you do, the more practice that you have. But let's start out with an example. Let me change my pen. The example is the square root of -16. I need to simplify that. So the way you do this is you break the square root of -1 out of the radical, and then you simplify. So what this becomes is the square root of -1 times the square root of 16. Notice how -1 times 16 gives you this -16, but what you've done is you've broken it up into a complex part and a real part. So what's the square root of -1? That was given to you. The square root of -1 is I. And the square root of 16 is 4. So when you are trying to find the square root of -16, what that gives you is I times 4, or just 4I. All right, let's look at example 2. In example 2, it has 5 square roots of -12, so that's 5 times the square root of -12. So when you break this apart, 5 times break out the complex part, square root of -1, and then we still have the square root of 12. So now when I go and I simplify for my next line of work, I still have 5. The square root of -1 is, and I can break up the square root of 12 into more factors. So think about what 2 factors give you 12. And your preference is to pick a pair of factors that has at least one perfect square. So I'm going to break this up. I could break it up into the square root of 2 and the square root of 6. So I'm going to break this up into the square root of 4 and the square root of 3. Because the square root of 4 is 2. 4 is a perfect square. So I have 5 times I times 2 times square root of 3. And any coefficients that I have on the outside of the radical, I want to multiply together. Same thing if I had more than one number on the inside of a radical, I would want to multiply those together and keep them under the radical. So here I have 5 and 2 outside of the radical. 5 times 2 is 10. The I is out. And then I have the radical with 3 as the radicand. This is my final answer. And I used some vocabulary that I want to make sure you picked up on. This square root symbol is also called the radical. A number inside, or at least a term inside, anything that's under the radical is called the radicand. So here 3 is the radicand. Here -12 is the radicand. -16 is the radicand. Here 16 is the radicand. So those are all things underneath the radical. Okay, let's look at example 3. Example 3 has the square root of negative 80. So go ahead and separate the imaginary or complex part with the rest of it. The square root of negative 1 is I. The square root of 80 can be broken up. It can be broken up into square root of 8, square root of 10, square root of 4, square root of 20, square root of 16, square root of 5. Those are all numbers that multiply to give you 80. So I'm going to break this up into the square root of 16 and the square root of 5, because 16 times 5 is 80. And the reason I did that is because this is a nice pretty number. 16 is a perfect square. So I have I times square root of 16, which is 4, times the square root of 5, which can't be simplified anymore. So if I reorganize this, bring my coefficient out to the front, my variable, my radical, my radicand. Beautiful. Okay, let's go on to a problem that has the same type of information needed, but it's a little bit different of a thing that's asked. It says you cannot have anything greater than I left in a problem for these examples. So I squared or any power greater has to be simplified. This is where that table at the top comes into play. So it says if you have I raised to an even power, so if you have an even power, then you want to write your answer as I squared and then use the power of 10. So I'm going to read this as I squared raised to some other power up here. When you raise a power to a power, the way that you combine them is with multiplication. So 2 times what gives you the 10? 2 times 5. Remember that I squared is negative 1. And negative 1 times itself, negative 1 times negative 1 times negative 1 times negative 1 times negative 1. Negative 1 times negative 1 is 1. Negative 1 times negative 1 is 1. But then you have this extra times negative 1 outside. So your answer is negative 1. And that happens whenever you have negative 1 raised to an odd power. These negative 1s pair off, but if there's an extra one left over to make an odd number of negative 1s, then you end up with negative 1 as your answer. So that's what happens if you have an even power. If you have an odd power, so I raised to power, you want to break it into I raised to an even power times I. And here's the reason why. If you have I to an even power, so let's say you have, let's say the original problem is I to the power of 9. You want to raise it to I to an even power times I. This is times I to the power of 1. And the reason that we're separating this, the reason that it's even allowed, is whenever you multiply like bases, you have to add the exponent. So 8 plus 1 is 9. And this splits up everything nicely so that I to the power of 8 can be treated like this. And then you can just multiply times I. So the trick is to take your odd power, bump it down by 1, and then multiply by the extra I that you bumped it down. So I to the power of 17, 17 is an odd number. So we're going to make this I to the power of 16 times what? Times I. I to the power of 16 can be written as I squared raised to the power of what? 2 times what is 16? 2 times 8 is 16. times that extra I. Well, remember, I squared is negative 1. So negative 1 to the power of 8 times I. Negative 1 to the power of 8, all my negative ones pair off, and I just get 1 times I, and that equals I. So we've simplified this as much as we can. It's kind of like trying to figure out what you would get if you used this in your table. So you know how it says the powers of I repeat in a definite pattern? We're trying to figure out if you had I to the power of 17, what would it be down here? So think about if you had I to the power of 9 and I to the power of 10. I to the power of 10 was what we found in our example 4. So it goes I, negative 1, negative I, 1. I, negative 1, negative I, 1. And then we would have I and negative 1 before we had negative I and 1. So I to the power of 10 is negative 1, and that's what we found down here. So it's just kind of trying to figure out if you completed the table, if you kept going, I to the power of this would be what? That's what it's asking. So go ahead and try example 6, pause your video, and then check back. Remember, when you have an odd power, you want to bump it down by a power and then multiply by I. You want to rewrite that I to the even power as I squared raised to another power. I squared is negative 1. If I times it by itself 13 times, I'm going to get negative 1. And negative 1 times that extra I out to the side is negative I. Okay. There we go. All right. So the reason that we talk about this is to talk about complex numbers. And complex numbers can be written in the form a plus bi, where a and b are real numbers. They could also be 0. But the b has the imaginary or complex component. So a plus bi, this whole thing is the complex number. The a is the real part, so real numbers, normal numbers. This bi is the imaginary part because it has I in it. So when you add and subtract complex numbers, you want to combine like real number terms and like imaginary number terms. So it's just like combining like terms in the past. So in example 7, I have 7 plus 3i plus 4 plus 9i. This is a complex number with a real and imaginary part, and I'm adding it to another complex number with a real and imaginary part. So I want to combine the real parts. 7 plus 4 is 11. I want to combine the imaginary parts. So 3i plus negative 9i is negative 6i. And there's my sum of the complex numbers. Remember that if you are taking a complex number and you're subtracting another complex number, you need to take that subtraction symbol and give it to both pieces of the complex number. So you should have 5 minus 6i minus 9 minus 8i. I'm going to give you a moment to combine your like terms. Your real component is 5 minus 9, which is negative 4, and your imaginary component is negative 6i minus 8i, which is negative 14i. So go ahead and pause your videos and try example 9. Check your work with mine. Make sure that you added or combined the real components, and make sure that you combine the imaginary components separately. So adding and subtracting complex numbers is not much different than combining like terms like you have in the past. When you multiply complex numbers, you want to try and distribute and multiply the coefficients and multiply the i's, the variables. So whenever I multiply, 5i times 3 is 15i. And when I multiply here, 5i times 8i is 40i squared. Remember that I squared is negative 1, so this is 15i. And then plus 40 times negative 1 is minus 40. It is a good idea to reorganize this so that you have the real component in the front. So negative 40 plus 15i would be your final answer. What about here? If you multiply 5i and negative 4i, you get negative 20. I what? Squared. That's negative 20 times negative 1, which simplifies to just 20. So it's possible that you'll get an easy problem like that, but it's also possible that you might have to multiply complex numbers using the FOIL method. You might have to combine your like terms, reduce some powers of I. So if you have an I squared hanging out, you might have to make them negative 1s, and then combine your like terms in the end and rearrange to make it look like a complex number. So I'm going to do one problem with you, and then I'm going to help you set up problem 14 for you to do on your own. So on number 12, FOIL. First, 2 times 7 is 14. Outside, 2 times negative 6i is negative 12i. Inside, negative 3i times 7 is negative 2i. And the last terms, negative 3i times negative 6i is positive 18i squared. So I'm going to combine these like terms that I have. 21i is minus 33i. And then 18 times I squared is really 18 times negative 1. So that's negative 18. And if I put 14 and negative 18 together, 14 minus 18 is negative 4, and I end up with negative 4 minus 33i. So it's very similar to foiling with an x variable. The only real difference, though, is making sure you reorganize. Make sure that you reorganize to make it look like a complex number. And if you have I squared, that becomes negative 1, so you can kind of simplify that term. So I'm going to let you try 13 and you try 14. However, 13 is the sum of 3 and I squared. So what that really looks like is 3 plus I times what? Another 3 plus I. And you have to be able to write it that way before you can FOIL. So pause your video and try examples 13 and 14 together. Go ahead and check your work, remembering that I squared turns into negative 1. So basically it goes away and changes the sign of that coefficient. So if you have plus 6i squared, that's going to turn into minus 6. If you have plus 1i squared, that's going to turn into minus 1. So let's move on to our last page of our notes. Simplifying radicals, including imaginary numbers. So the way that you want to do this is you want to separate, and we're going to write some stuff at the top. You're going to separate these into the square root of perfect squares and the square roots of everything left over. So separate. Into perfect squares under the first radical, and then everything left over in the second radical. And I do want to make sure that you know your perfect squares, so I'm going to list them out to the top and you can copy them if you see fit. So we are going to use these numbers at the top to break our radicand to perfect squares and everything left over. So in example 1, the square root of 176 can be broken up. 176 is actually the product of 16 times 11. Perfect square, not a perfect square. So I can break this up into the product of the square root of 16 and the square root of 11. The square root of 16 is 4. The square root of 11 can't be simplified. So you end up with an answer that looks like this. So now let's look at example 2. 54 can be broken up into 9 times 6. 9 is a perfect square, 6 is not. So I'm going to break this up into my perfect square radical and my everything left over radical. 9 times 6 is 54, but 9 is the perfect square, so it goes in the front. X to the power of 4 is a perfect square because its exponent is even. Y to the power of 7 is not a perfect square, but it can be written as y to the power of 6 times y to the power of 1. So perfect square, the leftovers. So now you can square root 9. You can square root x to the power of 4. So 4 divided by 2 is 2. And you can square root y to the power of 6. 6 divided by 2 is 3. And then you have your leftover radical with the leftovers in your radicand. Now, there is something that we need to mention. So when you take out in your perfect squares radical, when you end up having something that's like a variable with an odd exponent in your final answer, you're going to end up having to put absolute value around that variable with the odd exponent. And this is why. Let's say that y has a value of something negative, like negative 5, I don't know. And you take negative 5 and you raise it to the power of 3 and you get negative 25. And then if you were to have that here, your signs would be conflicting. And so you want to make sure that you have just the positive value of y cubed. So the positive value of whatever y cubed is, that's what you want outside of your radical. So I'm going to leave a little space down here to put a note that if you take an odd power out of an even root, then you need to put absolute value around it. Okay, so let's look at, instead of example 3, let's look at example 4. Because example 3 has a cube root, and so I want to do at least one more square root problem before we do a cube root problem. So if I'm going to split this up into a radical with my perfect squares and a radical with everything left over, and of course my coefficient out in the front that's already there, then I need to think about 128, and the numbers that multiply to be 128. So one of the things that you might see as a kind of consequence of trying to split these up into perfect squares and leftover stuff is that maybe you don't know all the factors of your radicands, of the coefficients. So maybe you need to take some time to do a little factor tree of 128. So 128 is divisible by 2. If I divide it by 2, 12 divided by 2 is 6. 8 divided by 2 is 4. And I could break this up even more, but I notice that 64 is a perfect square. So it's right here. It's 8 squared. So 64 is a perfect square. That's going to go in my perfect square radical, and the leftover is going to go in that second radical with everything else. X to the power of 5 is not a perfect square because the 5 is not even, but x to the power of 4 is a perfect square, and the leftover is another x, so that if you multiplied x to the 4th times x, you'd get x to the 5th. And then this is y to the power of 1. That's not a perfect square, and I can't make it a perfect square, so it goes in the last radical. So I still have -7 times the square root of 64 is 8. The square root of x to the 4th power is x squared. And then I have the square root of 2xy as my leftovers. So when I put all of this together, I have -7 times 8, which is -56, x squared, square roots of 2xy. All right. Now let's look at example 3. Example 3 is a little different because it has this. So instead of finding a perfect square and everything left over, I want perfect cubes and everything left over. So my 5 still hangs out here. It's my coefficient times cube root of my perfect cubes times the cube roots of everything left over. So anything in here needs to be either a perfect cube or a variable with an exponent that's divisible by 3. So I'm going to go ahead and write my factors of 24. My factors of 24 may be 2 and 12, and then the 12 can be broken up into 3 and 4, and the 4 can be broken up into 2 and 2. So I notice that these are it's like my prime factorization of 24, and there are 3 2's. 2 times 2 times 2 is 8. That's a perfect cube. The leftover is 3, goes in my second radical. M to the power of 5 is not a perfect cube. 5 isn't divisible by 3. But if I go down far enough, I can get something that is divisible by 3. So 3 is divisible by 3. And how many more m's do you need to multiply m cubed by to get m to the power of 5? The answer is m squared. You need 2 more m's. 3 plus 2 is 5. What about n to the power of 9? Is that 9 divided by 3? Yes. So n to the power of 9 is a perfect cube. So when I simplify this, I still have the 5. The cube root of 8 is 2. The cube root of m cubed is m to the power of 3 divided by 3, which is just 1. And n to the power of 9 divided by 3, which is 3, times all the leftovers, the cube root of 3m squared. Now I do have 2 coefficients that I need to put together. 5 times 2 is 10. M n cubed times the cube root of 3m squared. Now, I don't need to put absolute value around n cubed because I didn't take an odd power out of an even root. I took it out of an odd root. So I don't have to worry about that. Okay. So I do realize that this video is getting a little long, and so what I'd like for you to do is maybe I'll do example 5 with you because we do have a negative in the rest of these. So that means that there is at least an imaginary component under the radical. So maybe I'll do one more with you, and then you try the other ones by yourself, and you can check the answers with mine. So in example 5, 2i is still here. I am going to go ahead and take out my imaginary component, and then everything else is 40 p squared r to the power of 9. So I have 2i times square root of -1, which is another I, times my perfect squares and my leftovers. So 40 can be divided into 4 and 10. 4 is a perfect square, 10 is not. P squared is a perfect square. Ooh, I'm sorry. R to the power of 9 is not a perfect square because a 9 is not divisible by 2. But if I go down enough numbers, I can get something that's divisible by 2. That would be r to the power of 8. So the leftovers, there would just take one more r to multiply to get r to the power of 9. So I have 2i squared times the square root of 4, the square root of p squared, the square root of r to the power of 8, and then my leftovers. By the way, what is, oh, this should have been I squared. Maybe you caught that. Maybe you wanted to say, Miss Belsick, you forgot the squared. What is I squared? That's -1, right? So 2 times 2 is 4, times -1 is -4. P, r to the power of 4, square roots of 10r. This was an even root. I did take an odd power, so a power of 1, p to the power of 1, out of that even root, so I'm going to make that the absolute value, and that is my answer. So pause your video and try examples 6 and 7, check back for the work and the answer.